technologies like, for example, fluidized bed. The critical parameter for the bio-oil contamination is mainly temperature, whereas solid residence time and gas flow rate under certain conditions are not so relevant for the contamination. And also the reactor, the technology is flexible with respect to the different biomass tested by producing comparable results by changing the biomass. The microfiltration technique has been developed and successfully applied to reduce the bio-oil solid content, thus further reduce its contamination, but also the problems that in general solids can create to the catalyst in the subsequent upgrading step of the bio-oil. It was identified a regime of combustion where a stable and sustainable combustion of pyrolysis gas can be conducted, so it is possible to exploit this low calorific value fuel to help the energetic of the pyrolysis. And finally, the modeling part can provide indication on the final yield on the end products after bio-oil upgrading. Thank you.
Thank you very much. I don't know, can you hear me? No. Oh, right. Thank you. Thanks very much. And I hope we're going to have to move on to another presentation online. So I hope your co-worker can answer your questions. Thank you. Okay.
Thank you, Paola.
Thank you.
Paola was joining us from Canada, so appreciate the early morning for her out there. Okay, now we're over to Chris Kick. Chris, can you hear me?
Yes, I can. Can you hear me?
Good. Oh, wow, look at you.
Wow.
You look like an avatar.
Okay,
so when you can you share your screen?
Yeah, I'm trying to do that. Second. What screen do I share?
Your presentation, please.
No, do you already see some screen?
I can see myself.
That's good, I guess.
Okay.
Yeah. Now you can see the presentation, right?
Now I can see the presentation.
Yeah.
Yep.
Perfect. And you can hear me perfectly?
Perfectly.
Yeah. We can only see a small corner of your face, but that might be intentional. I don't know.
Not really, but is it better now? I cannot see myself, so I don't know.
Okay.
But
All right.
yeah.
Floor's yours then.
Yeah, thank you for having me. Even if I can only be there virtually, I'm glad that I can present the conversion routes in our European funded EU project, Phytoclimate. My presentation consists out of a short overview of the Phytoclimate project. I will then hop.
Before you start, there's a thing on your screen in the middle. I don't know what it says. It's in German. It's you might want to.
Is that better now?
Yes, better, much better. Okay.
Perfect. Yeah. Yeah. So as I said, my presentation has some parts, and first of all I will give an overview of the Phytoclimate project. I will then hop on to the biorefinery concept and the applied conversion technology, and then dive into our first conversion results, but also into the refinement results of the conversion products. And then in the end, I will give a short outlook and show some future steps. So Phytoclimate in a nutshell. Phytoclimate basically combines phytoremediation with biofuel generation, and the project started in 2021 and it ends in end of June 2025. It consists out of 17 partners and it stretches out of 3 continents and includes 4 pilot sites. Our part in the Phytoclimate project is basically the biomass conversion after it is harvested from the pilot sites and the subsequent refinement of the conversion products. Our pilot sites are basically located in Spain and Lithuania, mostly contaminated with hydrocarbons, but the pilot sites in Serbia and Argentina are contaminated with heavy metals, all above cadmium, copper, chrome, lead, zinc, and arsenic. And this is important because it's also important for the biorefinery concept, as we might focus and trap the heavy metals more in the biochar, as for example, if we only have hydrocarbons as contamination, we don't have to care about that. The biorefinery concept is shown on this slide as we understand it in Phytoclimate, and it consists out of two parts. The first is the biomass conversion itself, based on a pyrolysis system, which I will explain in detail in a little bit later. And a second step, the refinement of all those produced intermediate products using standard but also innovative refinement technologies to produce gasoline, diesel, and marine fuels. Coming to the conversion technology within Phytoclimate, the requirements the project has on the technology itself, and also the product quality we can achieve. Well, as I said, the conversion is done with an intermediate-based pyrolysis system called thermocatalytic reforming, short TCR. And it's a two-step process. In a first step, it's an intermediate pyrolysis based with an auger reactor where the biomass is broken down into biochar and volatiles in temperature ranges below 500 degrees. In a second step, those pyrolysis vapors will be led over the biochar with, at a temperature of about 550 to 750 degrees. And in this temperature range, the biochar acts as a kind of catalyst, breaking down further long-chain hydrocarbons, removing effectively tars by that, and also increasing the product quality, especially the hydrogen content in the syngas, which is significantly increased from around 3% to about 40%. So why TCR? Why not another technology? Well, first of all, it comes in Phytoclimate, it comes to feedstock flexibility, as we're using lots of different feedstocks for the phytoremediation process. And on the other side, it needs high product qualities, because only high product qualities allows a further refinement to biofuels. Speaking about feedstocks flexibility, well, as I said, in Phytoclimate, we're using different types of plants to remediate soils. For example, rapeseed, quinoa, sorghum, different mixes of herbaceous plants, and also Jerusalem artichoke. And with the TCR technology, we tested around 90 different biomass types, and they all worked. The biomass feedstocks had different chemical compositions, but also different textures, but it worked. The most important parameter is that they have a dry substance matter of above 70%, so they can be used in the process. Coming to the product quality, as I said, it's important to produce not any kind of intermediates, but to produce high quality intermediates so that they can be used to upgrade them to ready to use biofuels. So with the TCR technology, it's possible to produce syngases with a hydrogen content up to 40%, which is important if you want to use gas to liquid processes afterwards. Also, the oil we're producing is thermally stable, which means it can be processed in a classical oil refinery, which is also very important if you have a look on the economics of such a biorefinery. Because for small-scale plants, a decentralized refinement to full ready-to-use biofuels is probably not the way to go. And if it comes to biochar, we're producing biochar which is high in quality and can be used for different kind of applications, like soil applications, but also material or energetic use. Having said about the functional principle and the advantages of the technology, I want to show the units we have. So starting with the smallest unit, our lab scale unit, TCR2, which has a feedstock capacity of 2 kilogram per hour. And this is also the plant which we use for all the phytoclimate trials. But we also have a pilot scale unit with 30 kilogram per hour of feedstock. And then if you want to go big, we have a fully assembled and operational TCR 500, which means a unit which can handle 500 kilogram per feedstock per hour. And starting from the right of the presentation, you can see in green
Chris? Don't know if he's gone. I can't see.
I can hear you perfectly. Are you there?
Oh, here you are. We couldn't
Hello
see
again.
you.
I could hear you perfectly all
We
the time.
lost your connection.
So where did you lose me? Can you still see the presentation?
No, so you need to reshare your screen.
I'm very sorry about this.
No, don't worry, it's fine. These things happen.
Can you now see again the
Yeah, we can see
presentation?
the screen now. Confirm.
Okay, where did you lose me?
It's when you were pointing at the reactor. This one? This one, yeah.
Okay, that is our biggest unit, a TCR 500, which is able to produce to handle 500 kilograms per hour of feedstock. This was a plant which was built up within another EU-funded project called TuSynFuel. And with this plant, we were able to produce biofuels out of sewage sludge. So coming to our first conversion and refinement results, which we have gained in the phytoclimate project. For this, I want to show you again the biorefinery concept as it is in phytoclimate, first biomass conversion, and then individual refinement of all the intermediates we're producing. Our first conversion results of different feedstocks we've tested. In total, we did already 9 tests with 3 different feedstocks at 3 different post-reformer temperatures, ranging from 750 degree to 550 degree. And what you can see is that the higher the post-reformer temperature, the higher the amount of gas is you will produce. For the other products, it's vice versa. So the lower the post-reformer temperature, the higher the amount of biochar, aqueous phase, but also the oil phase will be. And this is important to understand this link between post-reformer temperature and mass distribution, as it gives you the ability to control basically the product distribution, but also the contamination concentration within those products. Coming to the refinement results, starting with the biochar, on the picture on the left, you can see the results from the Serbian pilot site where heavy metals was on focus. And you can see for different post-reformer temperatures, again from 750 to 500
Chris, we've lost your screen again, if you can still hear us. And we can't hear you again. Here we are. I can see you.
I don't know what's
It's
happening.
every time I move, I just need to stay still.
Yeah, that's probably. Okay, I'm very sorry to all of you. I don't know what's going on here.
Okay.
Getting there. Did you hear? So this was the last slide, right?
Yeah, we're with
Yeah.
you on that one. Yeah.
Yeah. So again, the refinement of the biochar is important because for heavy metals as soil contaminations, we want to make sure that we trap the heavy metals in the biochar. And for this, we were at the post-reformer temperature to see actually what is the optimum temperature to trap as many as heavy metals as we can in the biochar. And for us right now, in the initial trials, it's at 650 degree post-reformer temperature where we are able to trap most of the heavy metals. For other post-reformer temperatures, either if they are lower or higher, the amount of heavy metals trapped in the biochar seem to be lower. So we still have to do further trials to verify these results, and we're not sure why it is like that at the moment, but this is what results show. So coming to the oil refinement, because we want to turn the TCR oil into marine fuels, and we've done some trials to test this, and for this we used a simple lab distillation unit and had two boiling points, one at 150 degree and the other one at 250 degree. And on the tables on the bottom, you can see that the most important parameter for marine fuels, the kinematic viscosity, was for both distillates lower than for the highest quality marine fuel, which needed a kinematic viscosity lower than 14. We had 5, so that was good. Further steps are to test the full range of parameters which are in the norm of marine fuels and to see if the distillates also fulfill those requirements. Hopping to the aqueous phase, and I just want to make clear you all understand what we're trying to do with the aqueous phase in the project. So what we want to do is, first of all, to purify it in order to be able to bring it to a sewage system, but also we want to produce hydrogen and use this hydrogen as a feed in the subsequent gas to liquid process. First, purification results of the aqueous phase show that, which we made with the test stand on the right side, show that we can reduce the COD significantly by means of electrooxidation, bring it down to lower than 1,000 milligrams per liter, which is then allows us to bring it to a sewage system. And also at the same time, we could produce hydrogen, which we will then use. And now coming to the most sophisticated and technically difficult part in our biorefinery concept, and it's the refinement of the TCR gas to be able to use it in a gas to liquid process. And what we found out as we dived deeper and deeper into those processes was that there are various GTL processes, and all those process product qualities are linked to the sensitivity of the used catalyst. And this brings us to the point that if you have a very sensitive catalyst, it might not be economically feasible to do this refinement in a decentralized plant. Well, what do I mean if I say it's technically highly sophisticated? I mean the gas has to be purified very intensively. And we did that. We built a gas scrubbing unit, basically a very sophisticated one, containing 2 gas scrubbers in the beginning, an acidic and a basic one, for the initial cleaning of ammonia, but also hydrogen sulfur. And then we had subsequently 2 fixed bed reactors for the remaining hydrogen sulfur by using iron oxide pellets. We had 2 cooling traps, one for the removal of water and the other one for the removal of the remaining ammonia. And then we had 2 fixed bed reactors for the removal of basically anything else. That was highly sophisticated. And our results show that we can bring down the concentration of ammonia and hydrogen sulfur very significantly from initial concentrations of 3.5 mass percent of basically lower than 5 ppm. Also, we could show that we can bring down the relative moisture in the gas to nearly 0, applying this gas purification strategy. But with all this efforts, we were still not able to reach the thresholds for poisoning compounds for sensitive catalysts used in Fischer-Tropsch or methanol synthesis, because they require thresholds for ammonia or hydrogen sulfur in the ppb range, so like 1,000 times lower than we could achieve. And this is the reason why we then kind of try to find alternatives. And one of the alternatives is the so-called Synol process, a very old process, but robust. And the quality of the product it produces might not be as high as for the other products, because it only produces oxygenated hydrocarbons. But those hydrocarbons are already liquid, and they can be stored and they can be transported, and they can be upgraded in a classical oil refinery. So it's robust, but the quality is not as high. But we think that it will work compared to the other first planned GTL processes. And this is finally the biorefinery, how it looks right now, like basically learning from our experiments. We're not going to produce diesel and gasoline out of the GTL process, but we want to produce thermal stable liquid energy carriers and then upgrade those in conventional refineries. Further steps. Well, if it comes to conversion, we want to verify our mass and energy balances with biomass from the second and third harvest, so 2 are still coming. And also we want to verify and identify conversion parameters for different biomasses and soil contaminations, because it might make a difference what kind of product we want to produce in regards to the soil, to the initial soil contamination, even if it's
We've lost you again, or the screen. Don't know if you can hear us. We can't see or hear you, Chris. There we go. Back on. Okay. Okay, I'm back with.
Okay, I'm getting faster every time, but this might be the last time. Okay. So in regards to the refinement, we want to optimize our intermediate refinement, so through process parameter variation, so that we really are able to shift the contaminants between our products in regards to our requirements. And then we want to develop a mass and energy concept of the overall biorefinery. And finally, we want to align our technical possibilities, so all we learned right now from the lab, and bring it together with our identified business models from other work packages, so that technical possibilities and economics go hand in hand. And with this, I thank you all for my presentation. I am very sorry for this technical interruptions.
Thank you, Chris. If you can stay there just a couple of minutes, I think it would be
Sure.
the kindest thing to give you a chance, somebody to ask a question. It would seem reasonable before you vanish, literally. Okay. Is there a question for Chris?
Any questions? No.
There's one here. Thank you. Two. Oh, yeah. Thank you.
Thank you, Emma. I would like to understand, since you're not going to make diesel now and gasoline, what will happen to the hydrogen?
Can you speak a little bit louder?
What will happen to the hydrogen stream, since you're not going now to produce, to upgrade the intermediate to diesel and gasoline? What are you going to do with that?
Yeah, that's a very good question, and we didn't decide right now because this process of changing the concept of biorefinery is a very very new one, but we still might need it in those process, but maybe not all of it. So it's still to be decided.
It could be a product of the biorefinery itself, and you could sell it separately in this case.
I can hear you
Okay.
not very clear.
Okay. Thank you. Well, thank you very much, Chris. I think you can now go back into the ether. Okay.
Thank you for having me, and again, I'm sorry for the technical problems.
Thanks, Chris.
Right. Well, now I think we've got time for some more general questions relating to this afternoon's session, and then if there are any hanging over from this morning as well. So I think the floor is open for anybody to ask a question. So any specific question to any specific speaker? Right. Ana Luisa.
Thank you. It's working? Yeah. For you. Did you compare supercritical gasification with normal gasification?
Yeah.
In the framework of the Ceres project, it is not such a comparison necessary. Else, till now, I would say that supercritical water gasification is a special good for wet biomasses. But now we improved the process, and also dry biomasses can be treated by the supercritical water gasification. Thus, I have to perform a new comparison, but for me, it is well possible that supercritical water gasification will be feasible also economically at a scale of, let's say, 1 or 2 tons per hour, which is a good scale for decentralized applications.
And one more, just critical water. Have you tested?
Subcritical water. Yes, we had a PhD work performed some 10, 15 years ago, aiming to hydrothermal liquefaction. To choose a technology, pyrolysis, liquefaction, gasification, you should define what, like I have to have as product. This is crucial. Industry asks for electrical current.
Any further questions, please?
Yes, maybe it's a very simple question, but I was wondering, in phytoclimate, all the biomass that is produced is converted first to pellets and then sent, yeah. Well, in phytoclimate, yeah. And I was just wondering why that was, because in the other projects,
Yes,
Can you
where's
just repeat the question?
yes.
yeah, why not grinding it and just sending the biomass to the um,
I think that Chris would explain why pellets, because they insisted on pelletizing. I believe that pellets are feedstocks for the DCR.
Because special requirements of the length of these pellets and the moisture of these pellets, so it is probably due to the operating system for biofuel.
Anybody else? I'm sure it should generate plenty of questions.
Hey, I'm here.
Thank you. Most speakers didn't talk about what to do with the cadmium and lead that is remaining in our soil. The goal is to clean the soil, so what to do with these things? So all speakers had some slides about it, but it was not clear. One speaker had it about getting the lead with an electrode out of the solution, and the other one was using an acid solutions to remove the heavy metals, but still the heavy metals remain. So what to do with it?
Well, there's a suggestion there. You're going to make a suggestion about what to do with them. Okay.
A solution.
Oh, a solution. Okay.
Yes, thank you very much for these questions. The question is about the fate of the heavy metals. And in our case, one of our partner is Arubis. It's the world biggest copper recycling company. And in their process, they accept different kind of, let's say, heavy metal polluted material. And for one process step, they need, let's say, a kind of a layer based on coal, and this is mainly now done by coke. And in this project, we're gonna try to replace this fossil-based coke by this bio-based coke, which is of course contaminated with the
metals.
But in this process, it doesn't matter because, let's say, the entire periodic system is there.
It's still there.
They have a very specific process to get out these metals and concentrate them.
You make a very good point. I think the general issue is that you can't, there's no way you can destroy the metals. It's not like the organics that Jacko was advocating today, that you can. All you can do is stabilize and move around in the environment in one form or another. And that's a reality. And so it's something we have to think about. But it's a reasonable question what to do with lead and cadmium, because nobody really wants those. Maybe there will be a use, but one day again, but I don't think so. And they used to say that the solution to pollution was dilution. Well, it isn't. The solution to pollution is concentration, and that's what it's about, I think. Yeah.
Just a point, Alan.
Yeah.
For cadmium and zinc,
Yeah.
okay, I agree that it
Yeah.
exceeds the frequent value
Yes.
of the biomass. But for lead and copper, all the data that I've seen,
Yeah.
you have it in all the biomass.
Yes.
You cannot talk
You can't
about
get rid of
contamination
it.
of copper and
It's
lead
there.
because of the biomass. It's really the common range for any biomass.
Yeah. Yeah.
Most of the plants that we have seen are excluded.
Yes. Well, that's the main point. I mean, the grasses, all the energy crops as we've been looking at, they're all grasses, and they're excluder plants. So the metals are in the roots. Okay. Yeah. Yes. Sorry, I don't want to be a doom watcher, but
Can
you know.
you use roots for biomass for feedstock? Is it possible to use the roots?
Imagine that we have a field that is heavily contaminated with copper or chromium, then it might be interesting because it will be valuable just to
No.
Sorry, I was managing copper contaminated site for more than 40 years now. I remember that we have the orchard in France, in Italy. Everybody, the goal, everybody wants to remove such copper, especially using blanc. Even the French marigold was a dream.
Yes.
Yeah, it was totally fake.
Yeah.
What you can do is remove a bit of copper, available copper, in the soil using crop rotation like special sunflower line and tobacco, but tobacco is, it's very consuming. So sunflower is more useful because you have the biomass and some lime, you can have up to 100 milligram of copper in the leaf. It's possible. But sunflower, you need a crop rotation because due to the sclerotinia, you are not allowed to crop every year the sunflower. So you need a crop rotation. You disrupt the cycle of the fungi. Yeah, copper is really a change. It's not so easy.
No, I understand. Well, I think we agree with that. Yes. Yeah. Are there any more general questions? So there's one here. Yeah.
But don't forget selenium. Selenium you can phytoextract.
Yes, definitely.
Hello everyone. I'm from China, IBIC, and I have a confusion. I want to know because in the presentations with the biomass with pollutants in it can be produced into oil, biochar, and others. But I want to know how does the output and the input, is it economically feasible?
Yeah.
Who would you like to answer your question?
Because the lecture that this afternoon talked about the fusion, so every scientist can answer the question.
Can anybody answer that question?
I want to know the cost. Yes, and the output of the profitable. No.
Cost and profit.
Ah. Got it. Yes.
Okay, I will answer a little bit, and Jaco maybe can come because he was working on that. Looking on the work of Guillaume Echevarria for phytomining of nickel and agromining, of course, one of the drivers, it is the price of nickel ore, but it's interesting because in the case of nickel agromining, the quality of the nickel ore that you can produce is very pure and you have less impurity. And for the quality of the battery, it's very important. So the nickel metals that you can produce in the case of phytomining and agromining, it's interesting, and some European company like Aperam, ArcelorMittal, they are looking for that. Now, I know that Jaco, he can answer about the balance for cost because they were doing some work in Hasselt about the economy using tobacco, willow, energy maize.
In fact, for nickel, I have no data available. We did not have nickel contamination, so and for cadmium and zinc, the prices on the world market are very low. So the energy, it depends on the crop that you grow. Some crops, in fact, the input of energy is much too high, so that you don't have a positive balance. So, yeah, I cannot give you the data now. It is many years ago that we did that study, but yeah.
Well, thank you. That's a good try. Okay.
Not yet.
Not yet.
Not yet.
Well, do you want to? I think I'll just make one comment. Oh, good, marvelous. Okay. Well,
So
online. Yeah.
online. So the first question is, biomass resources are very important for obtaining future sustainable fuel supply. What is the energy and carbon efficiency in the presented technologies? For example, it seems that the last technology only had the range of 2 to 11% oil yield. So I guess, yeah, feed to climate again. Marcus is here. Any comments? Yes, about the energy and carbon efficiency.
I can answer that if you can hear me.
Oh, of course it's here. Okay, yeah, we can hear you. Yeah, please
Yeah,
go.
perfect. Yeah. So the energy efficiency is about 90% in regards to the energy of the feedstock you put into the system, and it's distributed accordingly to the mass distribution of the products. But in overall, it's about 90%.
Thank you. And just the last one here. What about hydrolysis towards sugar and lignin? Also, did anyone consider the special biomass plants? Harvest of biomass while wet, with carbonization and leaching, with gestate, carbonization of gestate and leaching. The last solution is well suitable for decentralized approach. So is that something that anyone's considered with the sugars and the lignins, or the carbonization of gestate and leaching? Perhaps that one. Okay, so for those online, those ones, the comments and things, we'll address those, and there'll be, with the recording, we'll put a comment next to those if there's anything comes out. So I'll hand over to Effie to wrap up the session. Yep. Thank you.
Thank you very much, Emma. So I think it's time to close the workshop. It was a great day, seeing 3 projects running together, almost parallel, with similar activities, but with difference also. And I think as a whole, we can make very nice, if we can collect very valuable information, because we are too many sites, too many technologies, and many different institutes throughout Europe, and not only. So I would like to thank you, first of all, the 2 coordinators that accept to be here and to make this idea reality. Thank you, Thanos. Thank you, Marcus. I would like to thank you, the invited speakers, for being here. Thank you. I would like to thank you, ETA Florence, for the great work in dissemination, Maurizio and Emma, and of course the whole ETA team that arranged the hybrid, that it was not easy. Alan Baker, being member of this advisory board, of course, special thanks to Maria Georgiadou for accepting to come for Brussels here for one day. Thank you, Maria, so much for the supporting all this year in all the events that we're doing. Thank you so much. Last but not least, I would like to thank you, Gold Team, and all this year that we have this excellent collaboration. Tomorrow we have our meeting, and I would like to thank you also, the CREST team, for helping me so much to organize all these days' events. Yeah. Thank you very, very much, and have a great afternoon. Well done. Bye-bye.
Well done. Well done. Yeah.